Hi. This presentation discusses the description of a capstone project proposing the development of a small music box. At the end, I expect you to be able to work with the very basics of music notation to explain the functional requirements of the music box using your own words and to plan the tasks needed to implement your solution using Vivado. The presentation comprises three parts: a short description of the context of this work, followed by a presentation of the overview and requirements, and at the end, a list of tasks to be carried out. Let's start by the context. What you are being asked to develop is a digital equivalent to the type of devices illustrated in this slide. You may notice that there is a closed digital equivalent to each element comprised in a mechanical music box. The rotating drum may be created with a memory where the cells corresponding to the spike positions hold a logic 1. The lever is the memory address generator. The different length blades vibrating at various frequencies correspond to modulus M counters, and so on. We will need a loudspeaker, but it shouldn't be difficult to use an FPGA to create an electronic replica of these music boxes. This slide shows the ascending frequencies in a C4 major scale for octave 4. An octave contains the 7 musical notes, and the frequency of any given note doubles as we move from one octave to the next. An 88-key piano keyboard covers a range of frequencies that extends through 7 complete octaves. Octave 4, shown here, starts with note C at 261 Hz, not kilohertz. As you would expect, octave 5 then starts with note C at double frequency, which in this case is 523 Hz. In the case of this project, we will limit ourselves to considering scales 4 and 5, meaning that the range of frequencies that you are asked to generate extends from 261 up to 987 Hz. Well, any audiophile will hardly become enthusiastic with our music box, but keep in mind that we are just aiming to replicate the usual mechanical device that is sold on souvenir shops. Even so, we will be able to use our 2 octaves to play any partiture as shown in this slide for Beethoven's Ode to Joy. So let's move on to the overview and requirements. Our melodies may be pre-stored in a read-only memory block coded into the FPGA fabric, but it would be more flexible to enable the sequence of musical notes to be downloaded from a computer into the FPGA using a serial protocol such as RS-232C. Then all we need is a play button to push when the melody has been downloaded and we want to listen to it. And here's a list of the functional requirements. You should support the generation of the 7 musical notes in octaves 4 and 5. Assume that all musical notes have a fixed duration of half a second, and use RS-232C to download melodies framed by control codes marking the beginning and end of the melody. What will be the tasks then? To start with, you should discuss and represent a block diagram for the FSMD data path architecture. This is a cornerstone of your project, since everything else will be derived from the data path architecture. Once it has been defined, you will be ready to design your ASMD chart representing the behavior of the control path. Create an initial draft representation by identifying the main operating modes, such as waiting for the arrival of ASCII codes, their storage in memory, waiting for the play button to be pressed, and so on. You will progress by refining your representation as you bring in more and more details, and in the end, all the control path inputs and outputs shall be represented in your ASM block elements. When the ASMD chart is complete and you feel confident that it correctly covers the full operation of the MusicBox, you have completed the most difficult part of your work. Anyway, with or without mistakes, you are ready to start coding, and you will need to follow a hierarchical structural approach, as usually for multi-block designs. Create a VHDL model for each data unit and for the control path, and create a top-level description to bring them all together. When everything synthesizes without errors, you will be ready for design verification. At this stage, you need to create the usual simulation source file. The RS-232 protocol is old and slow, although still used in various situations. You will probably choose to communicate at 19,200 bits per second, and at this rate the simulation would require a huge number of 100 MHz clock cycles. You have two solutions: sit and wait for the simulation to complete, or simulate subsets of the architecture independently. You may, for example, create a read-only memory with a pre-stored melody and just simulate its execution. Even though it may take a huge number of clock cycles given the low frequencies of musical notes and their fixed duration of half a second. But again, you can assume a much shorter duration just for checking if everything works, and then you will be a lot more confident when you put everything together. When your verification procedures give you confidence on your design, you will be ready to implement your solution. Create a constraints file using the master file of the Basis 3 board, generate the bit stream for programming the FPGA, connect the buzzer between your P-mode pin and ground, cross your fingers, and start experimenting. I wish you the best of luck, and may you have fun with this assignment. Thanks for your attention.